was gonna be asked to leave, be asked to retract my paper and so on, because it was so radical. And when the director of the conference in the middle of the week took me aside, I thought, oh no, here it comes. And I was really surprised that he asked me to stay for the award ceremony at the end of the week because my paper had won the Best Paper Award. And it had won the Best Paper Award based on a peer review panel of 11 scientists, mathematicians, and physicists, and so on. And the comments that came back from the panel were remarkable. So I'm very excited about this. And basically, the paper is a mathematical proof of the infinite nature of the atomic structure, the infinite nature of the nuclei of atoms, describing them instead as little quantum events, describing them in classical mechanics and gravitational mechanics as little singularity, little point of infinite nature. And how would I come to conclude that atoms are really black holes? And, you know, early, almost some 20 years ago in my research, I concluded that the center of all galaxies were black holes, and many other radical ideas, certainly at the time. And when I was presenting those at physics conference, they weren't so well received. However, since then, from telescopic evidence and astrophysics evidence has shown that the center of galaxies have been found to all host enormous black holes. As well, my theory predicts that black holes are the source of the formation of galaxies, not the result. The standard model would think of black holes at the center of galaxies being created by a bunch of stars colliding and accumulating and eventually reaching a critical mass necessary to produce a black hole. My theory says that no, that black holes were there before, that the black hole is a phenomenon of the structure of space-time itself, of the structure of space, and that the material world, or in this case, the accretion and the production of material that makes up a galactic disk and a galactic halo, is the result of this dynamic in space-time that we call a black hole. These conclusions came to me early on because of the obvious logic that tells us that space can be divided to infinity. And let me just give this simple example. Here on the screen we have a circle, and in the circle we put a triangle, an equilateral triangle. Now this example is shown here in 2D, but it could be a 3D example. The sphere could be, the circle could be a sphere, and the triangle could be a tetrahedron. And I'm assuming that in this group I don't have to explain what a tetrahedron is. And since the universe seems to exhibit spin at all scales, we are justified to reverse that triangle because of polarization. Interestingly, right away, as we do this, we get one of the most common ancient symbols found in many, many different cultures around the world. For instance, this symbol is found in the heart of all the statues that represent the Buddha with his chakra system. And from there, we can discover that from doing this, we've reproduced the same geometry at the next fractal level down, at the next iteration down. Now, this boundary condition that we just generated, it is very important to understand that these new boundary conditions are identical in nature, but that they're all individualistic because they all are in their own very specific coordinates of space-time. No boundary in the system is in exactly the same coordinate system. So each one is a complete individual. However, it is bounded, it is related to all other geometries by its own fractal function. So if you polarize that field, then you obtain smaller boundaries again. And you can do this again and get smaller boundaries and so on and so on. And if I continue to do this with a computer, I could get it to zoom in every 5 or 6 boundary and continue to divide and zoom in and continue to divide and so on towards infinity. Actually, it will never end. It will continue to divide this space. However, it would never, ever, 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 ever exceed the first boundary that I've made for myself. So here, in the context of a finite space, I obtain infinite amount of division possible, infinite amount of information. And this is really important to understand. It is an infinite amount of information because each set of boundaries, like we said earlier, identify a very specific coordinate in space-time, thus is observing the universe, is observing the structure from its own very specific perspective, gathering a very specific set of information. Thus, each boundary represents a new set of information, and I can compactify infinite amount of boundaries in this system. And so here I show that there is an inherent relationship between boundary conditions, between what seems to be a finite space and infinite curvature, infinite division, infinite density. And since infinite amount of information means infinite amount of energy, there is great possibilities and great application and understanding to this approach. This approach as well changes our concepts of the physics that are written and the physics that are experimented with. For instance, by simple understanding of this geometry, we would most likely stop attempting to find a fundamental particle, some small quantity, some small particle, and call it the God particle, and start looking for a fundamental pattern of division instead of a fundamental piece of the atom that's supposed to be the fundamental block of creation. For decades now, we've been building larger and larger devices, accelerators, to get atoms to collide and make smaller and smaller and smaller bits. And, you know, I believe there's no limit to this based on this example. We can continue to divide the atom in smaller bits, build larger accelerators. Although we've reached practical limits now, the Hadron Collider in Geneva in Switzerland is 17-mile long, cost some $13 billion to build. Every time we turn it on, it breaks because it's so strong. Many of the materials there are unable to deal with the strength of the magnetic field, and so on. And I believe that we can continue to break the structure down, but it's not going to tell us anything about how it got there in the first place. That more importantly is to understand the pattern of division, the structure. And here, when we look at this example, we realize that actually the material world could be the result of a simple division of the space itself. And here, I think, we could make a thought experiment. Well, our current model of the universe looks a little bit like this. This is out of gravitation. Gravitation is the Bible of relativistic equation, and it was written by Wheeler, Thorne, and Mesmer. On page 719 of this book is the typical model after a few thousand equations of our current universe, of our observable universe. And the model is a balloon that's been expanded, and the example glues pennies to the surface of the balloon. And the pennies represent galaxies, and as the balloon expands, the galaxies move away from each other. However, in this example, nowhere in all of the equations is there an equation that describes this guy. And that's what I wanted to know. Who is this guy? Because without that guy blowing the balloon, without that guy compressing the air inside the balloon, then the balloon cannot expand. The universe cannot do what it's doing. And this part of the equation, the guy that's blowing the balloon part of the equation, is widely overlooked. If we continue to draw the guy, then we start to get a hint on what we need to pay more attention to. Because as the balloon is inflating, as it expands, then we can clearly see that the lungs in the person blowing in the balloon must contract. For every action, there is an equal and opposite reaction. And which part of the universe is the contractive part? Which part is the part that compresses, that actually organizes the structure so that it can eventually radiate? That part has been overlooked in our current physics. There is a radiative part, but there is an entropic part, and there is a general active or syntropic part that organizes in order for things to eventually radiate. And we see this in nature everywhere. Obviously, the biological world, our biosphere, is highly organized. It's very efficient at compactifying systems and communicating between systems in order to create very complex, very advanced structures. For instance, a human being has inside its cells the equivalent of 5 million times around the world in DNA. So if I took all the DNA inside one human being and I put it end to end and stretch it out, uncoil it, put it end to end, I could wrap it around the world 5 million times. That's the amount of information compactified, even just at the biological level, that allows for all systems to coordinate and communicate and generate the complexity we see. And there is approximately the same amount of DNA in a shovel full of dirt there is in a human being because of microbial life. So it's highly organized, it's highly compactified, and that part of the physics of creation is typically ignored. Well, when we start to think this way, we start to wonder, well, if the radiative world is the atomic, the physical world, what is the contractive part of the equation? And if I was to ask this question, if you were to try to find something that connects all things, what would it be? Well, the only result you could get eventually, as you thought about it, would be space. Space is everywhere, it's in between everything, and it is even at the atomic level present in a quantity of 99.99999%. So all of the material world you're looking at is mostly space with 0.0000001% of this little oscillation, this little boundary condition, this little electrostatic field that's oscillating, and that we call the material world. And actually, nothing ever touches anything, just a field interaction produce our material compounds and so on. So mostly space, and early in my young youth, I started to wonder, maybe the material world is the result of the space, not the material world defining the space. So instead of matter defining space, space may be the source of matter. And actually, this is really one of the first steps that's stated in this paper that I just published. And that's very simple, 8-page paper with some 16 equations. And it defines the vacuum structure as the source of the atomic world. Now, let's take a look at it in a little bit more details. If this was true, then the vacuum, the structure of space, would not be empty. If space is the source of the material world, then space cannot be empty. It would have to be full, extremely full, since all atoms, all material world would be radiating into space. So the space, in one sense, would contain infinite amount of information, since it's receiving infinite amount of radiation from all objects in the universe, all combined in the structure of space. So here's a very important statement. This is found in gravitation as well. Present-day quantum field theory gets rid by renormalization process of an energy density in the vacuum that would formerly be infinite if not removed by renormalization. And that is because when you look at an oscillator and you try to figure out what is the waveform interaction and how much energy is present in the oscillation structure inside the oscillator, you run into a problem that you can divide the waveform interaction to infinity. So there's infinite amount of energy present. But since that's not an acceptable result in quantum theory, to think of the atom having, or the space inside the atom, the vacuum structure having infinite density. Because when we think of the vacuum, we don't necessarily, and I'm not talking about the vacuum you're cleaning carpets with, the space, we don't typically think of it as infinitely dense. However, we know that the space carries electromagnetic fields and, all sorts of energy levels. And here we're seeing that it may be the source, the carrier of the fundamental energy level of creation. So here was a confirmation that the space may be the source of the material world. Well, what is renormalization, however? Well, when we found that the space at the atomic level seems to be infinitely dense, and since this was not an acceptable result in physics, there was an attempt to renormalize the number. And that was done with the Planck's distance, and the Planck's distance being a computation done using gravitation and the Planck's constants and all this stuff, which is eventually turns out to be very close to a phi ratio. Most people haven't noticed that in physics. The Planck's distance is 1.616 multiplied by 10 to the minus 33. So it's extremely small, billions of times smaller than the atom, and it's thought that the Big Bang, or all of our universe, emerged from a dot that small. The only difference in what I'm saying and what they're saying is that I'm saying that this dot exists at the center of all atomic structure, and the Big Bang, the bang is constantly occurring. We call it our material world. This distance, the 1.616, I believe, should be modified to 1.618, since it's a phi ratio, and phi seems to be present everywhere in nature. So this calculation is a little bit off of the standard model. However, this singularity, this point of infinite density, is thought to be the smallest thing the universe does, the smallest electromagnetic fluctuation possible in the structure of space. And thus, and you can think of it as the time it would take a photon to go across itself, if you want an analogy, a simple analogy. So they took this, believing that it's the smallest thing the universe does, and if you ask me my opinion, I would tell you that I believe that there is fractal division below that dot, but that dot, that boundary condition, is one of the fundamental boundary conditions that defines our world because of the scale of observation that we take on our universe. Meaning that if our scale of observation was much smaller, was at the Planck's distance, then we would see resolution past this boundary condition. So if what happened here in renormalization is that they said, well, let's take a centimeter cube of space, then let's stack it full of little Planck's distance, and instead of an infinite amount of oscillations in the oscillator, we will have a finite number. So they stack the cube full of little Planck's distance, and since each one has a mass of 10 to the minus 5 gram, the computation gives us a density for the vacuum fluctuation inside a centimeter cube of space. That density is 10 to the 93 grams per centimeter cube. Now, this is an extremely large number. This is 10 with 92 zeros following it. And if you've all noticed in your bank account, whenever you add a zero, things get big very quickly. And so when you compute this, you realize that actually the vacuum density inside a centimeter cube of space exceeds the density that you would have if you took all of the stars in the universe, every single one of them, out of all the billions of galaxies that we see, and you stuck them all in a centimeter cube of space, what would be the density of that cube? You can imagine it would be extremely high. However, it would still come shy of the density of the vacuum by 39 orders of magnitude. You'd have 10 to the 55th gram per centimeter cube, which is 39 orders of magnitude less than the density of the vacuum. That is, you would have to still add, after 55 zeros, 39 zeros to get to the density of the vacuum. So what we think of as the empty space around things, around us, around, your chair, around, in the room you're in, so on, that to think of that as empty seems to be incorrect. Now, you may say, well, does this really exist? Well, or is this a mathematical computation that's useful in quantum theory, but that is, not realistic in the real world? That number is used. 10 to the 93 grams per centimeter cube. It's called a Planck's density, and it's used in quantum theory all the time. It's absolutely necessary for our computation to occur properly, and um, at this point it has been verified in laboratory. That is, the Casimir effect has shown that you can get two plates together close enough so that you can eliminate the long wavelengths of the vacuum and get them have them on the outside of the plates, but not on the inside of the plates pushed together, and that the plates are pushed exactly at the rate predicted for such a dense vacuum. So it is there, and it is extraordinarily large. Now, if the statement that the vacuum structure is the source of everything, that basically when the vacuum divides, the material world emerges. When there's a little oscillation in the vacuum at a certain rate, you get an event horizon, you get a boundary condition, then it would be clear, and it should be, that when we do a graph of universal size objects all the way down to the subatomic particle of the universe, that the data points should line up. There should be some evidence of structure. There should be evidence of connection or correlation between things. It wouldn't be just random. The vacuum structure would divide under very specific harmonic relationships. And that's precisely what we did. Dr. Rasher and I took various sizes of objects and their frequency, their energy level. We plot them on a graph and radius against frequency, and they all started to line up, starting with the universe here at the bottom. And by the way, if you take the 10 to the 55th grams of our universe and you stick it in the space that we observe our universe to be, our universe obeys the condition of a black hole, obeys the condition of a singularity. And, so we are living inside a black hole. And then the next thing we see is our quasars, and then galactic centers, and then solar star, like stellar objects. And all these, when you plot them, start to line up quite nicely. Then we jump from the relativistic world, which is not supposed to agree with the physics of the quantum world, and we jump to the atomic size and its energy level, and it lines up perfectly again. So here we have evidence of unification between the quantum world and the relativistic world. And unification is a set of equations that has been sought for a very long time. Actually, Einstein spent most of his life believing that his equations of relativity could solve for the atomic structure. However, quantum theory that he actually had initiated got more and more popular, and although he didn't agree with some of the fundamental principles of quantum theory eventually took over and basically threw our physics into the physics of some kind of illusionary world in which things don't have energies, don't have sources, where you don't need to explain the causation of things. You just throw quantum numbers and start doing calculation. You don't have to explain where the spin of anything came from, where the energy to produce the atom came from, or anything like that. And here we're going to see that I think that Einstein was right, and that his equation could solve for the atomic level, except that you have to consider the atomic level as a mini singularity, which when Einstein's field equation predicted black holes and singularities, at the time, that sounded so radical and sounded so implausible that it was thought that that part of the prediction of the equation could be ignored, and that black holes probably wouldn't ever get found, that there was no such entity in our universe. However, eventually black holes did get found, and as I mentioned, at the center of all galaxies. And now what I'm about to prove to you is that not only are they at the center of all galaxies, they're at the center of all atoms, at all the center of all atomic structure. Now, we continue the graph with the last data point here showing that the Planck's distance lines up. You know, the singularity lines up perfectly. So now we have a graph from universal size all the way to the Planck's distance, extraordinarily large scale, and in which all of the data points in between line up nicely. Here showing very clearly that there's a sense of organization, there's a system in the division of the space. If we look at the relationship on the graph to the right here of the division, then we find that these relationships are phi ratios, are very, very close to phi ratios. Appropriate, how do you say, approximation, considering the enormous size or scale relationship between these objects, and obviously the approximation that have to be done in the measuring of their size and their frequency. It's remarkable how close we get to the phi ratio and its reciprocal. So when we look at this, interestingly, we see further that if we plot microtubules, which are little entities, little spiral tube structures that makes up the membrane and the skeleton of your cellular structure, of the biological resolution. When we look at those microtubules and we plot them on there, they nicely line up with the rest of the universe on the scale, almost bisecting the scale in the exact middle, showing that the biology, even the biological entities, are part of this division of the space, of this relationship between all objects in the universe. The biological entity is one of the event horizons from which all information moves through from universal size to the atomic level. You are part of the information network of the universe. You are absorbing information from the vacuum, and you're feeding information back into the vacuum in this continual feedback loop of information transfer at all scales. And I know that's a lot to take in a very short amount of time, but let me get into the details a little bit on how can we actually start to consider the atomic resolution here as mini black hole. Note again that the Schwarzschild condition, which is the condition of a black hole, which was a solution to Einstein's field equation, matches both the Planck's distance and the universal size. Those two can be considered black holes, literally, when you put the mass in the equation. So does quasar, so does the galactic center, and certainly stellar objects that collapse in the standard model in black holes. In this model, stars are already black holes. We're just seeing the radiating side of the event horizon. We call it a star. And here I'm about to prove that the atom is actually a singularity as well. Basically, we live in a universe of different scale black holes, different scale singularity. It is clear to me, philosophically, that if you were to find one black hole with one singularity, from that moment on, you could not conclude that the universe is divided ever again, since if you find one singularity, that even the word, the concept of singularity is that it is singular. That is, that it has infinite curvature. So any objects anywhere else in our universe would be part of this curvature of this point that you just found. So you cannot divide anything anymore. Everything would have to be connected through that singularity. So here we've seen that the vacuum density is extraordinarily large. It's 10 to the 93 grams per centimeter cube, and that's been verified in that report. So in this paper I just published that won the award, I said, well, okay, if the vacuum has this density, how much of that vacuum density of a centimeter cube of space is still present inside the atom? Is there enough energy in the vacuum structure inside the atom for the atom to actually be called a black hole? Because if you said to a standard physicist today, the atom is a black hole, the first thing he will say or she will say is, that's not possible, it's not dense enough, there's not enough energy. Well, that's if you're not considering the energy present in the vacuum inside the atom. So in order for us to do this, we have to figure out what is the volume of the nuclei of the atom. I placed the equation in the context of the proton, the nuclei of an atom, which has a radius of 1.3 Fermi, which is 1.3 multiplied by 10 to the 13. And so what I'm asking, the question I'm asking, is how much of the vacuum density, how much of the energy of the vacuum is still present in such a small volume, which is, you know, very, very small, millions of times smaller than a centimeter cube of space. So it's very, very, very teeny, this teeny little dot in the middle of the atom. How much vacuum energy is still present in there? So in order to do the calculation, we have to calculate the volume of the proton.